We've developed a number of techniques for analyzing translational motion of particles as they move around. But what about if we want to analyze the motion of spinning things that have some length to them, like these wind turbines? We need some additional tools that we'll develop right now with analyzing fixed axis rotation. We'll start by defining some variables, comparing them to the translational quantities that they're going to be similar to, and essentially redeveloping everything that we did for translational motion again for rotational motion. That means doing the kinematics, which is how the motion is related to itself, how acceleration, velocity, and position are related. Now for rotation. And then figuring out what makes things move, the kinetics of why they're moving, which for translational motion was force, and for rotational motion is going to be torque. And we'll be able to develop Newton's second law and apply it to rotational motion. First, let's get some variables. We'll start by trying to get position. We had position for translational motion, so we'll have it for rotational motion. In any of this rotational motion, we're going to want to use radians because they give us the ratio of the length around a circle to the radius of the circle. The length subtended by an arc here around the outside of a circle is equal to the radius times our angle in radians. That means 1 radian will equal 1 radius here for our arc length s. That means we can relate the length around the outside as shown here. So this is the definition of how this arc length stuff works. We just make sure that we put this in radians and s will equal r theta. We'll point out that 1 revolution, a complete way around the circle, is equal to 360 degrees. In radians, that's going to be 2 pi radians going around the circle. We have position, now we want displacement, and we'll define displacement as we did before as the difference between initial and final position. So far so good, we have position displacement. Next, let's develop velocity. Our average angular velocity will be the change in our position over time or our displacement over time, and we'll use the Greek letter omega to refer to this. This is the Greek letter theta, so we'll say omega bar is equal to delta theta delta t. If we want to compare that to a translational quantity, this is similar to how we had our average linear velocity, v bar, equaling delta x over delta t. And just like we did with translational velocity, we can take the limit as that delta t goes to 0 to get our instantaneous angular velocity of d theta dt. This is similar to what we did with translational velocity, where we had v is equal to dx dt. Now we have omega is equal to d theta dt. We have position, displacement, velocity, and now we'll do acceleration. It will look very similar. Our average angular acceleration is now going to be the change in velocity over time. For angular quantities, this will be the Greek letter alpha. That'll be alpha bar is equal to delta omega over delta t. And that's similar to how we had our average linear acceleration as delta v over delta t. As before, we can take the limit as that delta t goes to 0, and we get alpha is equal to d omega dt, which you can daisy chain with our previous relationship to say that then that's the second time derivative of position with respect to time. And that's pretty much the relationships. There's one other thing to mention here, which is that we have some tangential motion on rotating bodies that we can define using these quantities here, where we have tangential velocity is r omega, and tangential acceleration is r alpha. This is similar to how we had s was r theta. If you start with that and say that my velocity is ds dt, where s is that length around the outside of the circle, my velocity is the change in that position over time, then we can substitute in s equals r theta, do a product rule, and take the derivative of the first times the second plus the first times the derivative of the second. And as long as we're staying at a constant position r, then our change in r over time is 0. Our radius, our distance away from the center of rotation is 0. That will be true for a rigid body. As long as this body here is not shrinking or expanding, whatever point we consider will stay the same distance away from the axis of rotation as we experience this fixed axis rotation. Which means that we can then say that we're left with r d theta dt, where that d theta dt was omega. Similarly, we can say that our acceleration in the tangential direction is going to be r alpha.